So good morning, everyone. Hope you're all right. So another Monday morning with VLSI. Today, the plan is to look at what's called pipelined ADCs. They evolve out of the flash ADC that we looked at last time. Yeah, there are never any questions, but if in case there are any questions from the last lecture, please ask before we get started. I do one or two of you prefer to write emails, which is okay, but it's better to ask questions in class. I hope to schedule, we'll have at least 2 sessions that will be dedicated to questions and exercises and past paper questions. So I'm aware we haven't done that, but we'll do that soon enough. So we'll probably just get stuck in it. We'll do this by example. We could start. Oh, Yihong, if you can't hear what I'm saying, you won't be able to read what the transcription does. My accent is not quite standard English, so I'm afraid I have to decline that because it's not useful. But you can get, when you look at, because this is, you can access this recorded lecture via Moodle after the lecture. And this one will have a transcription. I don't have time to correct it, but if you're desperate for that, look at it after the lecture. So we'll start with an 8-bit ADC, which is called a sub-branching ADC. It's also called a 2-step. It can be multi-step, but this particular one is a 2-step ADC. And we do that with an example of an 8-bit ADC. In an 8-bit ADC, we have an analog, sampled analog input. And from this analog input, we need to determine the bits B1 to B8. And the relationship between the two is this, which we know B over 2 squared plus B3 over 2 cubed plus B4 over 2 to the power 4. I write this out because it's important for understanding how this architecture comes about. B5 over 2 to the power 5 plus B6 over 2 to the power 6 plus B7 over 2 to the power 7 plus B8 over 2 to the power 8. In this 2-step ADC, first we determine B1, B2, B3 to B4. And yes, first we determine that using a flash ADC, for example. So we do that in 1 step. And if we did that, that means our V in, we approximate it with the Vref. That's the approximate V in. Will be approximated with B1 over 2, B2 over 2 squared plus B3 over 2 cubed plus B4 over 2 to the power 4. And there will be an error voltage which corresponds to the contribution of the other 4 bits if we had them. So the way we do this is our error voltage will be equal to our input voltage that we actually got out, minus the approximate voltage, which is Vref, B1 over 2 plus B2 over 2 squared plus B3 over 2 cubed plus B4 over 2 to the power 4. But since Vin, we are looking to represent Vin by 8 bits. So the input voltage ideally is represented by that expression, but we're only determining the first 4 bits initially. So if we put this expression in here, it means that our error voltage is B5 over 2 plus B or 2 to the power 5, B6 over 2 to the power 6 plus B7 over 2 to the power 7 plus B8 over 2 to the power 8. So it's actually this expression. So we have our sampled input voltage. We have the equivalent digital voltage that we're looking for, comprising 8 bits. But instead of getting the 8 bits at the first go, we first of all just get the first 4 bits. So if we did so, the error voltage will essentially be equivalent to the final 4 bits. Of course, this would be times Vref. And so this expression looks a bit like that, but it's not quite the expression of an ADC. So I can factor out 2 to the power 4. And if I do that, I can write this as Vref B5 over 2 plus B6 over 2 squared plus B7 over 2 cubed plus B8 over 2 to the power 4. And you should be able to notice that that expression is the expression of a 4-bit ADC. So out of this, I'll draw a block diagram that helps us to do this. So if we know this expression, we can determine B5, B6, B7, and B8 using a 4-bit ADC. So from those equations, what we're saying is that if we have Vin, which is represented by 8 bits, actually come into a block diagram there, which I leave. Oh, my pen has given up light. I need to get another one. So here I could have a 4-bit flash ADC. And the output of this, out of the 4-bit flash ADC, I can get B1, B2, B3, and B4. So in one clock cycle. And these bits, I can input them into a DSC. And I'll get the approximate Vin. Vin that corresponds to the first 4 bits. At this point, I can get my input voltage. So this is my Vin. If I get my Vin and I subtract that from those 4 bits, what comes out there will be V error. So the input voltage into this summer comprises of the actual input voltage, and the actual input voltage, we want to represent it with 4 bits. We've approximated, we want to represent this with the 8 bits. The approximation there is 4 bits from the first ADC. So we approximate it with 4 bits. We get the analog equivalent. The original sampled voltage is 8 bits. And if we come into this summation and we subtract this approximate voltage from our actual input voltage, what we get here is the error voltage. And that error voltage will be equal to that expression. And that expression, we know we can write it like this. That means that if we amplify the error voltage by this factor, so if I come into, if I amplify this by a factor of 2 to the power 4, then the output of the error voltage is this particular term, which we can put into a 4-bit as the input of a 4-bit flash ADC. And the output of this would be B5, B6, B7, and B8. And for this, all this, the reference voltage for this conversion is the same. The reference voltage there is the same, and the reference voltage for that first bit is the same. Up with sample and input. I'll talk in a minute about this block. The sampled input is here. We sample and hold it. The sampled input, we'd like to represent it with 8 bits. So my V-in, or the 8-bit V-in, that's the value there. But first of all, we represent it by 4 bits, and we can use a 4-bit flash ADC to do that. So in one clock cycle, we get those 4 bits. After that, we get the analog equivalent of the 4 bits that we've determined. We subtract that from the 8 bits, and the expression that we get here will be equivalent to the final 4 bits. But for us to use an ADC to do that, we need to amplify that by 2 to the power 4. I hope it's clear why we need to do that. I mean B5, B6, B7, and B8. In terms of how long it takes to do this, so for the 4-bit flash ADC, we need 1 clock cycle. For the DAC, I'd like to someone for the DAC, if someone can say how long it takes to do the conversion back into an equivalent analog signal. The amplifier, someone should also say how long that it takes. And the 4-bit flash ADC will require 1 clock cycle. So can I get probably someone who hasn't answered a question in class before? The DAC, how long does the DSC? We didn't talk about time when we were looking at the digital to analog converters, but how long does it take to do the conversion? If we use clock cycle as our unit of measure. And this is one of the MSc students. How long does the DSC, if we have the 4 bits, how long does it take to convert the 4 bits into the analog equivalent voltage? One of the MSc students, please. Okay, one of the BH students. Let's start with you guys first. Four clocks, hang you. Now, for the DSC, the DSC doesn't need 4 clock cycles to convert the 4 bits into one into the analog equivalent. If you remember, the DSC, it's either weighted capacitor, weighted resistor, and the switches are connected correctly depending on whether it's a 1 or a 0. So it shouldn't take 4 clock. For the ADC, we need, okay, for the flash one, we need only 1 clock cycle. I would say this is less than 1 clock cycle. That's also less than 1 clock cycle. For the DSCs, the conversion, you could say it's instantaneous, but not quite, because the signal needs to travel through the op-amp or the comparator. So yeah, but it's pretty fast. So here we'll need probably this type of architecture. It's called that. So we do 2 steps to get the bits. If this is a flash ADC, it's 4 bits. We need 15 comparators. If you understood the last lecture, or have revised it. If not, you can double check that. We'll need 15 comparators. We'll need, I think, 16 resistors. And because we have 2 4-bit flash ADCs, this one times 2. So that's the size of the circuit. So the size is still a bit fairly big. But if you compare to an 8-bit flash ADC, if you did this just with an 8-bit flash ADC, it will require 2 to the power 8 minus 1, which is 255 comparators. And it will require 256 resistors. So it's a much bigger circuit if you compare it with a flash ADC. Yeah, before you go to the pipeline architecture, I hope I don't need to show the circuit of a DSC. We should all be familiar with that. Or an amplifier, we should all be familiar with that. It shouldn't take a clock period for the signal to be amplified. It takes the time delay for the signal to go through the amplifier, but that's what's the trade-off? Yeah, so between flash and so we go for the flash ADC. The circuit has probably 3,000 transistors. Each comparator has like 10 transistors. So this circuit altogether, it's but it will do conversion in 1 clock cycle. If you go to the 2-step comparator, you reduce the circuit, the chip size significantly, and also the power comparison. Yeah, I'm getting the message that my connection is unstable. This lecture I'm delivering. How do we proceed? I could talk slowly and give time. It's the UniWi-Fi, so this you know how the UniWi-Fi works. I cannot reset my router. It's all set up by the university. Alternatively, I can log out and log in. Everyone will all log out and log in again, because we're only 20 minutes into the hour. Shall we do that? Okay, I think we all log out and log in again. So I'll just end this and then restart again. Hopefully it will be a better connection.